is Chris Pattison, who's going to tell us about hierarchical memories. Please take it away.
Thanks. So this is joint work with Ani Krishna and John Preskill. I guess we heard earlier today about how kind of we have the BPT bound. We can also construct memories that maybe saturate the BPT bound in 2 dimensions and 3 dimensions and so on. But actually, here I'm going to tell you that it's that the that saturating the BPT bound is not actually the best that we can do. What we really care about is what is the rate for some amount of error suppression. So I'm going to construct memories for which we have a local implementation, but the codes themselves are not necessarily geometrically local. So obligatory. So what's a LDPC code? A quantum LDPC code, and it's just one where every check is constant size, and each qubit participates in just a constant number of checks. And importantly, good QLDPC codes exist. And we've had constructions of this for a few years now. And why we care about this property is it gives us a few nice things. One is it automatically gives us fault-tolerant syndrome extraction. And kind of today, the theme is going to be mostly syndrome extraction. And what we know is that under depolarizing noise, with a min-weight decoder, kind of there's this result from Kovalev and Predko that tells us that any LDPC code with polynomial distance has a threshold. And then furthermore, usually our QLDPC code constructions come equipped with like an efficient decoder. So that's usually quite nice. And then finally, there's this result from 2014 where Gottesman showed that you can achieve constant space overhead computation if you have what I like to call OK parameters. That is, that we have constant rate, but maybe only like polynomial distance. Okay, so kind of in some sense, locality is a curse. So physics is geometrically local. If we have 2 experimentalists separated by distance d, as the experiments are separated, kind of there's no way that I know of to have a constant strength interaction between these 2 boxes as we bring the boxes further apart. But this isn't necessarily a bad thing, because it also means that we can easily isolate our system from the rest of the universe, right? If this experimentalist here is over maybe on Mars and this one's on Earth, then probably they shouldn't be highly coupled, right? That would be quite bad for us. So, okay, you might say, well, what if I just pick up the box, move it there, and then move it back? Well, this kind of works only like non-asymptotically. Kind of the qubits in my box maybe have finite coherence time or something like that, or maybe I shoot photons from one to the other. But kind of fundamentally, like the photon is going to have some fidelity that's going to decrease with the size. And all this is to say that we want some model that approximates what we can do in practice. And right now, kind of the constants are such. So likely in the future, we're going to be operating somewhere in between, kind of where we're not fully 2D, but we don't have like this arbitrary connectivity that we typically assume, for example, in classical computation. In classical computation, it's very cheap to move a bit across some potentially fairly large distance. So for today, I'm going to consider a model where we have only 2D gates, and classical computation I'm not going to worry about, but let me focus on the quantum gates. So and then at the very end, I will mention how we can get to this like in-between regime. So, okay, so what's the main result? Is if we're given a good LDPC code family, quantum LDPC code family, and we have this, we have noise in our experiment, our quantum computer, that is what we call locally decaying noise. So you can think of this as we're permitting some amount of correlation in our errors, but not too much. Sort of that for any set of our qubits, the probability that the error is a superset of the set is exponentially small. Sort of if we just had like IID noise or something like that, we'd have equality here. And so it's kind of a loosening a little bit. So if we have like a gate error that kind of takes out a few different qubits or something like that, but for example, like a constant size, this is fine. So, okay. And what we do is we construct a family of codes for which we have rate that's polylogarithmically going to 0, but still like quite good, and distance that's also polylogarithmically going to 0, relative distance, sorry. And the syndrome extraction circuit has, and we also construct syndrome extraction circuits that have this nice property that it's using only nearest neighbor gates on some 2-dimensional lattice. For convenience and to get like the best constants, we pick that it's actually a 2-layer lattice, but this is not fundamental. We can just as well remove this 2 and have just a regular square lattice if you like. And I guess the most important thing is that with repeated syndrome extraction and correction, using a minimum weight decoder using this syndrome extraction circuit, we have a failure rate we have a threshold, and below this threshold we have sort of this exponential suppression of the logical error rate per syndrome extraction cycle. So kind of the standard things that you would need for example, if you're to run this in a if you're to use this for like a computation or something like this. So okay, how does this compare? Well, so and let me say that I'm only comparing with memory for now. Kind of for the most part, the difficult part is just having something that we can store our logical information, and that's kind of the first step to being able to manipulate it. So okay, so the first sort of thing that we can compare to is say surface codes. It's 2D. It only uses 2D connectivity. It has geometrically local checks, and it has this trade-off between the rate and the error suppression. Sort of that a rate that we have kind of if we want constant rate or anything close to constant rate, we're going to pay by having almost no error suppression. So okay. Now, what about good quantum LDPC codes? We're going to need long-range connectivity, and our checks are only local, not geometrically local. But we have constant rate and exponential error suppression, which is quite nice. And then our result kind of sits somewhere in the middle. We have 2D connectivity. Our checks are not geometrically local, but that's fine. We can still measure them. I'll describe how to measure them later. And we have, again, this polylogarithmic loss in parameters versus the good codes, which is quite nice. So, okay, so fundamentally, what's the issue with geometric locality? So we know of this result from Delphos, Beverland, and Tremblay, that there exists a space-time trade-off for syndrome extraction circuits of good codes. Roughly, if we have a syndrome extraction circuit that uses the minimum amount of memory, then we're going to pay a price. And this price is kind of this polynomial depth. Roughly the intuition for this is as follows. If I take my Tanner graph of my code and I embed it into a 2D lattice, and I can take any embedding, this holds for every embedding, and I consider 2 regions, A and B, that in my 2D lattice, sort of the volume of this region is, well, it's the volume, but the perimeter of the region, the surface area, is only a polynomial of the volume. Kind of it's actually just significantly smaller. And this is really, really problematic because if we compare this against code bounds, then we start to run into trouble. So we know of this. So there's this nice series of code bounds by Noid and Bapin and Ani Krishna. And what it says is that essentially for good QLDPC codes, we have that for any subset of vertices of our Tanner graph, the number of vertices that are adjacent to it is of size proportional to it. So kind of, if you compare these two things, what it says for our embedding here is if I have my two regions, A and B, is I'm actually going to have a ton of connections that between these. Sort of, I'm going to have some qubit over here that's going to need to do a gate with some qubit over here, and there's going to be a lot of them. And in fact, there's an amount that's proportional to the volume here. So if you kind of look at this, you'll say, okay, well, for each edge that crosses this cut, I'm going to need to consume a gate, and I can only do square root of this volume number of gates per unit time across this cut. And so I conclude that I require square root depth in order to measure everything here. So okay, but this is a statement about the depth of our syndrome extraction circuit. It doesn't necessarily preclude you from having a threshold, and indeed it doesn't. So what's the strategy that we're going to take? Is that we're actually going to do a fairly trivial approach, which is that we're just going to say, fine, I'm okay with requiring that we do these long-range gates, and I'm just going to simulate this long-range connectivity. And there will be a problem that we'll later fix. So the way I'm going to do it is I'm just going to assign, say, arbitrary sites in my 2D grid, and say I'm going to do an entangling gate between those two sites that are maybe nearest neighbors, and then I'm going to permute the support of that gate to that site, and then apply the gate. And I'm going to do this for some constant number of rounds in order to measure the checks in my LDPC code. And so the way the actual proof goes is I'm going to start with, so I have this relatively deep syndrome extraction circuit, and I'll tell you how to construct this in a moment. I'm going to have a lot of qubits. And then to achieve a threshold, for the threshold results that we have, kind of the threshold theorems, we require that the noise accumulated per syndrome extraction has to be a constant. And actually it has to be a constant that's sufficiently small. So actually O1 isn't, we need something a little bit stronger than that. We need a constant upper bound that's, maybe 10 to the minus 3 or something like this. And so, okay, that's kind of a problem. But we know a syndrome extraction circuit is itself, we know how to suppress errors in circuits, right? This is what we do already with fault tolerance. So let's do that. We'll just take our qubits, replace every single one with surface codes of size that's like logarithmic in the original block length. And this blows up our lattice a little bit, right? So previously I had square root n, and now I have square root n times a polylog factor. But that's, and this polylog factor will come back a little bit later. Roughly that's, in some sense, you may believe that I can do logic and then we'd be done. But this is a little bit of a longer talk than that, so we can get into it. So first, what I'm going to do is to tell you how to construct these syndrome extraction circuits, and then I'm very briefly going to discuss the replacement of the qubits with surface codes. So, okay, so how do I construct syndrome extraction circuits? So for each, so on the right, I've drawn the Tanner graph of some code, and on the left, this is kind of the standard syndrome extraction circuit for measuring an XXXX operator. So what I need to do is I need to assign to each check an ancilla qubit, and then find a scheduling of the entangling gates. So I'm going to do that. And the trick is I'm going to apply what's known as a graph edge coloring. And this is kind of a standard technique. And because the Tanner graph is bipartite, this edge coloring can be found efficiently. So this graph edge coloring has the property of that for each vertex in the graph, the edges of no two edges of the same color are incident to the same vertex. So these colors actually tell us exactly which gates we should apply and which time step. So for example, here, I'm going to apply all the red edges, sort of a C0 gate between my data qubit and my ancilla, then the green edges, and then the blue edges, and then the yellow edges. And then I'm going to just measure the ancilla. And then you repeat this procedure with the Z checks, and this is one way to get a constant depth syndrome extraction circuit. So, okay, great. Now I need to embed this into 2 dimensions. And to do this, I'm going to get, or rather, sorry, I need to be able to bring the targets of my entangling gates close together. And to do that, I need to do routing. And so this routing task reduces to something known as a permutation routing. So the sort of abstract problem is that I have a graph, and at each time step, I can apply swaps along the edges as long as the subset of edges is a matching of the graph. Sort of that I'm not that I don't have swaps that have that share the same support. And so I have my labeled pebbles, and I need to get them to certain other addresses. So for example, I need to get 1 down to 1. So that's what multiple time steps of this permutation routing problem would look like for just the line. And we use this nice result of Annexstein and Baumslag from 1990, which tells us, given, so if we know how to route along 2 graphs, G and H, that we actually know how to route along the product graph, the Cartesian product, with not too much loss in the parameters. Sort of what we're going to do is we're going to use the routing in both of these graphs as subroutines for the full thing. So for example here, if I have 2 qubits, this blue qubit that needs to go up here, and this red qubit that needs to go over here, what I'm going to do, so the naive strategy would to say, oh, let me just route them to the necessary row that they need to go to, and then the necessary column. But this is problematic because both of these qubits need to go to the same row. And so what the Annexstein-Baumslag algorithm does is it takes an extra step in G to avoid this issue. So what we're going to do is we're going to take first a step in G, such that these are in different columns. Then we can route them to take the step in H, and then we can take the step in G again. And so I'm going to use this routine a few different times. So let's see what it looks like for the two-dimensional graph, or two-dimensional lattice. So first, I need to tell you how to route on the products. Well, I can route on the line quite straightforwardly. This is so to route on like a line graph, I just need to use what's known as an even-odd sorting network. This is from Knuth's book. You'll notice here that the time here is actually optimal. So this is the longest distance that any pebble needs to travel in a permutation is L-1. And that corresponds to shuffling this number 1 pebble all the way to the end. Great. So now I'm going to route on the product. So that's what this looks like. So I have my 2D lattice, and then I have sort of the world line of the qubits. So you see here, I do some routing in the rows, routing along the columns, and then routing along the rows again. And so the time to route is roughly 3 times L, where L is the side length of the lattice. So okay, great. So I've told you how to simulate the long-range CNOTs. And so essentially, in some sense, the syndrome extraction circuit up to this detail about the surface codes is kind of fully defined. I will note that this is everything that I've presented here, except for the minimum weight decoder, is all efficient. So these are efficiently constructible. So our last ingredient is a surface code. And so really, in order to believe the asymptotic result, you only really need to know some asymptotic properties of it. And these properties are perhaps not so surprising. Here I've drawn some surface codes on a lattice to give you an idea of what this actually looks like. So if I have an L by L surface code, I know how to do essentially full universal logic with it in a 2D implementation. And really what I need is I need to be able to do Clifford operations between nearest neighbors in the lattice with polynomial resources. So for example, I need to prepare like computational basis states. I need to be able to do C-naughts, and I need to be able to measure. Okay, great. And surface codes have a threshold. This is not a surprising fact. And sort of the point is that you have an exponential suppression of the logical error rate with the size of your surface code. So okay, so because we have this exponential suppression, we're just going to pick this polylogarithmically sized surface code. The noise in our syndrome extraction circuit per round is kind of now, if we picked this polylog appropriately, it's a constant as we grow the code family, and so we've recovered a threshold. So great, we're perhaps done. So now we can consider, you might say, oh, well, what about the constants and such? In our paper, we construct very low overhead layouts for how to do like swap and C-naught and everything you like. So this is an example of one such construction for how to do the C-naught. It's not important, but if you want, you can look at the paper for that. The point is that this is very low space overhead, and we try to minimize the number of in-cell qubits that we have in order for the constants to work out. Like asymptotically, we'd like to be able for this to work in sort of the non-asymptotic regime. And also, given some gates of maybe some longer range, we can also tunably interpolate between sort of the long range gate regime and the short range gate regime. And I'll get to that in a moment. And so for now, if we want to talk about practical applications, we need to have a decoder that's practical. Our threshold proof uses a minimum weight decoder. But we can also do something quite nice, which is, so in 2006, David Pilon had a paper on concatenated codes and showed that if you have a decoder that has some idea of how good or bad its correction was, you can pass this information up to the next level in the concatenation and decode and get better decoding performance. And sort of quite naturally, for most LDPC code families, kind of the practical decoder is BP, and this takes a prior. And then for a surface code decoder, we can attempt to extract soft information from this. And that'll be the subject of some further work. And just to recap, we had some syndrome extraction circuits with our long-range gates. We simulated the long-range gates in 2D, which cost us this depth blow-up. And then we cured the noise that appeared using these polylogarithmically sized surface codes. So we had sort of a coarse-grained analysis using some techniques from Gottesman's 2014 constant overhead paper. And we got these parameters, and we had a local implementation. So I want to end with two nice extra bits. One is that so far I've been talking about the setting of just purely like local gates on a 2D lattice. But if you give me some tunable range in which I can do gates, so for example, maybe it's like some photonic platform, or maybe it's some modular architecture like we saw in Ted's talk this morning. Or maybe I can like move my qubits in some way where it's kind of asymptotically, I'm still stuck with 2D, but maybe locally I have some long-range gates that I can do. So we can exploit this fact and fully tune between these two regimes. So we imagine that we have this range R that we can do the gates. And this, unfortunately, is a very dense graph. It has roughly a vertex degree like R squared, something like this. So what we want to do is we want to find a sparse subgraph of the connectivity graph here that has constant degree. So we can do this and for which we know how to route on. So we can do this by just replacing this with a spectral expander. And we know how to route on spectral expanders by using this result from a Long-Chung and Graham. And the idea is roughly that you take like a random walk on the expander, and this gives a routing. And this gives like log. So this gives us a log routing. So okay. So then we take the subgraph that is a product of our expander, kind of inside some fixed region, and then we have sort of the 2D structure sort of asymptotically. And so, as one might expect, kind of the world gets a factor of 1 over r smaller, which is quite nice. Sort of this is the lattice length, and this is the distance of our gate, and this holds for any r as long as you don't make it like actually. There's some subleading terms that I've suppressed, but you can imagine for any r here that's like not. That's subleading in square root n. This holds. So okay, and then finally, I want to end with sort of this other quite nice idea, which is that you may ask, like, okay, so we've gotten to 2D, and we're almost at like constant rate, and you might ask, like, okay, is this polylog factor fundamental? And because I'm presenting this in a talk, the answer is no. And kind of the main observation is that we needed these surface codes to suppress the errors while having a 2D implementation, right? And these surface code had this kind of nasty error suppression and rate trade-off. Well, it doesn't have to be the surface code. It just has to be any code for which we have a 2D implementation. So why don't we just use a hierarchical code to sort of bootstrap our way up and to get better and better hierarchical codes with better rate. And so indeed, we can do this, and then we can improve this 1 over polylog to quite a bit better than that. And with that, I'd like to conclude. Thanks.
So when you route the atom, the qubits, do you spread the error as well?
Right, good question. So the important detail is that the majority of the gates, we're still applying a constant number of entangling gates. And so a swap gate kind of fundamentally doesn't spread error, fortunately. It can fail and create a correlated error on the 2 components, and we handle this. But fortunately for us, kind of in some sense, we have just a really, really complicated idle step where the qubits are laying idle for a fairly long time. But there's a lot of opportunities for errors to appear, but they're not spreading, fortunately.
Can you help clarify? So is the bilayer architecture a requirement? Like, do you need 2 levels? Because I'm presuming you're using a transversal CNOT in order to avoid the ancilla.
That's right. Yeah. So we have a version of our proof that we actually initially proved this using lattice surgery in a fully 2D layout. That's one way to remove the bilayer architecture. The other way is to kind of like emulate the 2 layers in 1 layer at the cost of threshold.
So I guess the kind of the related questions is, does the ancilla incur significant cost, right? And is there a way to directly use the ZZ measurements from lattice surgery instead of needing to do CNOTs?
That's a good question.
Because it seems non-trivial that you would need so many ancillas kind of just lying around in order to facilitate that.
Right, yeah. So at one point we did investigate kind of well, what if we paid more in Scillas and just did like a direct sort of lattice surgery measurement of each stabilizer generator? And it seemed to us that this was not kind of the space-time cost would blow up in that case. It wasn't obvious to us that we could get the same sort of nearly optimal space-time cost.
Is that even the case if you did a multi-body lattice surgery operation?
I believe so. Because kind of fundamentally it's multi-body, but like still constant weight. Constant weight from the perspective of the surface codes.
Okay.
Can you comment on the speed of logical operation and the logical cycle time?
Yeah. So one way so one obvious conclusion is that our cycle time would be quite slow. But kind of if you have, for example, a single shot code family, and you look at the error exponent, then it's actually perhaps even faster than asymptotically faster by operating your an LDPC code in like a single shot setting than just doing like D rounds of error correction in the surface code.
You still need to do the permutation, which is slow, right?
That's right. It's slow, but it's of order of the size of the lattice length. But that lattice length is going to be logarithmic in the size of the computation. And in a surface code, it needs to be, I think, logarithm squared. Or there's a square root somewhere there that you pick up.
Okay, so it's a polylog depth.
That's right. Yeah. Yeah.
Any more questions?
Polylog depth in the block length, which is log.
Could you just comment on when you apply this inductive construction at the end, what parameters you end up getting? Or if,
Better than polylog.
So if I open the Gottesman's paper on 2013, then it basically uses 7-qubit code to prepare logical code words of LDPC code and so on like that. If you replace 7-qubit code part with surface code part, then you obtain your protocol to understanding. Then it will be rather straightforward to have all the logical gates in the same way. Am I correct, or am I mistaken?
Yeah, so kind of fundamentally, if you take any LDPC code family for which we know how to perform logic, that immediately ports over to what we can do. So in fact, there are applications to computation, and kind of we're looking into this. I guess the main difference is that we explicitly have to consider the layout and such, which so it's in one sense it is just you could think of it in this way, but there's a lot of work that you have to do in order to get the 2D layout.
Yes, yeah. Thank you.
At least to my understanding.
Yeah, I'm just curious. This polylog overhead sounds really swell for the like purist side of me, but for the like someone who has to actually do something at a company side of me, like what's the crossover point at which this polylog actually starts to become competitive with like real qubit numbers?
Right. So so in order to have a good estimate of this, we need to run numerics with these more optimized decoders that use the soft information. We need to consider code families that are more modern. We did like a very, very basic back of the envelope analytical calculation with hypercorrect product codes that assumed kind of like maximally damaging hook errors, which we now know not to be the case, and kind of minimum weight decoders on both source and on the outer code. So our conclusions were mostly that the word error rate at which the asymptotics kick in is not too bad. It's not like 10 to the minus 100 or something like that. It's like if you wanted to build a memory of word error rate like 10 to the minus 15, you may want to use this coding strategy. but what sort of block lengths are relevant in order to for this to make sense is still kind of open. But potentially a moderate size.
Any more questions? Okay, if not, let's thank Chris again.